just have a couple of announcements. One is that, as we mentioned in the email, unfortunately our second speakers today had to cancel due to illness. The other announcement that I wanted to make is that we've already had one cancellation due to travel restrictions associated with the coronavirus. There are chances that we'll have additional cancellations kind of in the future because we had some speakers who are also coming from Europe. And so we're looking for additional local speakers who might be interested in filling those slots that may open up. So if you have a talk that you've given elsewhere, or just want to put together a talk, or have a talk coming up and you'd like to give it here as practice, please contact me, Francesca, or one of the other organizers of the seminar, because we're looking for volunteers. And with that, I am very excited to welcome our first speaker, Eva Laplace, and Sebastian is actually going to introduce her.
So thanks everyone for coming. This is Eva Laplace. She's currently a grad student at the University of Amsterdam, working with our own self-domain, where she works on supernovae and massive binary evolution models and how that relates to gravitational-wave astronomy. She does have a background in observations. She got her master's in Japan working on X-ray observations of X-ray binaries. And she is on her second to last year of the PhD. She will be applying for postdoc next semester. She's going to be visiting us all of this week and all of next week. She'll be happy to come up to you, and she's next to Selma's office in 2 to 6. And with that, go ahead.
Thank you. Yeah, thank you for having me here. So, as Sebastian already said, my name is Eva Laplace. I'm a PhD student at the University of Amsterdam. I work with Selma de Mink, who is a new faculty here, and also with Stephen Justin in Amsterdam. And my work is on the life of strip stars, stars that are stripped in binary systems, how they die, and what the consequences are for gravitational wave sources. So if there is one thing I would like you to remember from my talk, it is that binarity affects the life and the death of stars. So let's see if I can convince you of this. So what are the big questions nowadays in stellar physics? So we have, how do stars evolve? How do stars die? What do they leave behind? And what about binaries? Right? These are the big questions we're trying to address nowadays. And today, this age is really an incredible time because we are entering the golden era of optical transient surveys. So there has been, in the recent years, an explosion of optical transients facilities. I'm just listing a few here. I'm sure I'm forgetting a lot of them. And there's many others on the way, or that have already started observing. And just to give you an idea, LSST, one of the biggest upcoming projects, is going to see 1,000 supernovae per night. I don't know if you realize how big this number is. Like, a supernova, typically a galactic supernova, happens every few hundred years, right? So 1,000 a night is completely going to change our view of the universe. And there's another incredible advance in the field from recent years, and that is the first successful explosions in 3D. So in the last few years, many different groups have finally been able to explode stars in multi-dimensions. And so it's really the right time to try to understand supernovae. There has been also a lot of advances from theoretical models, lots of pioneering work that I'm listing here. And still, theoretical stellar models are scarce. Even with the samples we have today, we cannot explain many of the transients that we see with the current stellar models. And this is where my work comes in. So I work on this subset of supernovae that I call stripped envelope supernovae. These are core collapse supernovae, so supernovae that mark the end of the life of massive stars. And these are really interesting because they don't show the most abundant elements of the universe. So many of them don't show or show only very little signs of hydrogen, the most abundant element in the universe. Some of them don't show any trace of helium, the next most abundant element in the universe. And they're classified in this really weird way of 2b, 1b, 1c that is, can be a little bit confusing. So why should we be interested in stripped envelope supernovae? So first, stripped envelope supernovae are extremely common. They make up a third of all core collapse supernovae. This is a very large number. And that's a quarter of all observed supernovae. Also, something that is often overlooked is that these are important for gravitational wave progenitors. So this diagram you see here is the typical evolution of an isolated massive binary system, all through the different steps of interaction until it forms a double neutron star system that merges because of the emission of gravitational waves. And there's many different steps in this diagram, but what I want to highlight is this. There's two steps that involve a supernova. And both of these are stripped envelope supernovae. This one is known as a typical stripped envelope supernova, typically a 1b. This one, ultra-stripped supernova. So understanding the properties of these supernovae might also let us know more about the progenitors of gravitational waves. So stripped envelope supernovae obviously come from stripped stars. And there's two main ways of how we think stripped stars can form. So either through very strong winds in very massive single stars, or through binary interaction. And what you get left behind is basically a helium or a carbon-oxygen core. In this talk, I will focus mainly on the binaries. If you want to hear about why I think binarity is important for explaining stripped envelope supernovae, please ask me. I can explain it in detail later. Okay. So my project for my PhD is to make stellar evolution models using the stellar evolution code MESA. It's a 1D open source code that has been used very much in the community, and trying to understand the consequences for gravitational wave events, for supernovae explosions, and for supernovae light curves. So today I will mainly focus on the first part of my work and just briefly highlight some recent results on the two second ones. And if you're interested in the first part, my paper is on arXiv today, so please have a look. Okay, so to start with, let me briefly recap stellar evolution. Okay, so how do stars evolve? How do they look like when they die? So what you see here is a Hertzsprung-Russell diagram. So luminosity as a function of temperature, hot is on the left, cool is on the right. And these diagonal lines give you an idea of the radius of these stars. What you see here is the standard evolution of a massive 10 solar mass star. And so it burns hydrogen into helium on the main sequence. It leaves the main sequence, becomes very, very large. Then it climbs up the hierarchy track and dies as a red supergiant here, with 1,000 solar radii, roughly, in size. So now what happens if I take exactly the same star, but I put it in a binary system? And the star that is next to it is slightly smaller. and in a typical orbit of 25 days. So the beginning of the evolution is very similar. Evolution on the main sequence, the star becomes more luminous as it burns hydrogen into helium. Then it leaves the main sequence, burns hydrogen in a shell. And as it expands, it becomes so large that it can fill its Roche lobe. And at this point, something dramatic happens. It's called Roche lobe overflow. And basically, the star transfers its outer layers to the companion star, which results in this dip in luminosity. And then the inner hotter layers are exposed. The star becomes extremely tiny, becomes a strip star. And here, it lives for a very long time as a core helium-burning strip star. And actually, it is a source of ionizing photons. But this is not the end. So at the end of its evolution, it expands again. And it dies here in a stripped envelope supernova explosion. So exactly the same star, if it lives alone or with a companion, has a completely different life and a completely different death. So many people are not very familiar with tracks on the HR diagram. So I thought I would show you a movie, because that's typically more clear. So what you see here is the radius evolution of a star. For reference, you have the HR diagram on the left again. And the color gives you the effective temperature as it is perceived by the human eye. Okay. So the star evolves on the main sequence, becomes larger. Now it becomes so large that it fills its Roche lobe. It transfers matter. Still tries to stay in the Roche lobe. Becomes much, much smaller. And here, you still see a dot. Okay, I cheated. You shouldn't be able to see a dot. It's so small, so tiny, impossible to see. Okay? This is a strip star. And then, at the end of its life, it expands again. And it dies at approximately 30 solar radii. Okay. So, I hope I could convince you that binarity affects the life and the death of stars. So I just want to stress here, I'm not the first one to point this out. I got a very funny email this morning about my paper on archive from a Russian colleague who pointed this paper in Russian to me that maybe I should have been aware of from the 1970s, where they did similar evolutionary tracks. It's really beautiful. Look at this. It's hand-drawn. And yeah, to understand it, I would need a Russian speaker. So if anyone speaks Russian, please help me. Yeah, so I think it's really nice to see the history of this field. It's not the first one, though. So the first pioneering work was done by Rudolf Kippenhahn in 1967. Okay. And yeah, so gravitational wave events. Let me tell you about this. So as I mentioned before, the paper is on archive, so please check it out if you're interested. So what I did here is use our updated code with all this updated microphysics to try to understand the evolution of these strip stars as a function of mass and metallicity. So what you see here again are evolutionary tracks that are very similar to the one I showed you before of these stars that get stripped in binary systems. And what I was interested in here is how much they can expand. And I will explain in a minute why this is important. So the color gives you an idea of the initial mass. So stars that have low initial masses will die at cooler temperatures than stars with higher initial masses. Now, when we go at lower metallicity, it becomes much more interesting also for gravitational wave progenitors because we mainly see them from a low metallicity environment. And you can see that they expand much more, right? In principle, that can die at a radius of about 600 solar radii. And these effective temperatures are very, very similar for all masses we consider. So why is that so? What is different at lower metallicity? So the interesting thing is at lower metallicity, the stripping process is less effective. So when you transfer matter, it is not so easy to remove the outer layers. That has to do with the opacity being different in the star. And this means that at the end of the mass transfer, some hydrogen can be retained. And this hydrogen is extremely important in being able to drive this later expansion of the stars. So to give you a better idea of these differences, sorry, I think this doesn't work. Okay, I had a movie, but it disappeared, so that's fine. Okay, so for the size comparison, we can look at this later. So why is this important again for the gravitational wave progenitors? So remember this evolutionary track I showed in the very beginning. So this typical evolution from an isolated binary system up to the progenitor of gravitational wave radiation. There is a few steps that involve strip stars. And how much they expand really determines how likely it is that they will interact again. And when stars interact, when they transfer matter, typically they don't only transfer matter, but also angular momentum. And this is very important. As you transfer angular momentum, the entire orbit of the binary also is affected. And typically for these stars, the orbital separation of the stars shrinks, and so the stars get closer together, and it is more likely for them to be able to merge within a Hubble time. So why is this important? Most of the calculations that I made to try to infer the rates of gravitational wave progenitors rely on simplified prescriptions for all different steps in stellar evolution, because they have to. So these population synthesis models, they typically simulate a billion stars, let's say, in binaries, and they try to see how many of these become double neutron star systems and how many of these become double black hole systems or something else, and try to get the rates out of this. So obviously when you simulate this large number, you have to make simplifications. And so the way they do this is to make fits to detailed stellar evolution models and try to use analytical prescriptions to make the simulations faster. So what I will show you here is, as a function of the final mass, what the maximum radius is that is assumed in population synthesis models. So all of these rely on the calculations from that were shown, so on prescriptions in early 2000 that are based on detailed stellar evolution models from Paul's 1995. So when I compare the models that I showed you before at solar metallicity, we see very similar trends. So at higher masses, the radius goes down. And at lower masses, it becomes larger. The difference is not so large at the high mass end, but between 2 and 3 solar masses, you can see a difference that is about an order of magnitude. And this might seem small, but it is actually really important. Why? Because these low mass stars are really favored by the initial mass function. So even in a such tiny range, this difference in size will have a large impact. And now when we go to low metallicity, now there is a very, very large difference. So you have 2 to 3 orders of magnitude differences in size. And you could tell me, oh, yeah, well, this is clear because this is lower metallicity, so let's just compare it to the prescriptions for low metallicity. Well, there is no prescription for low metallicity. That's the whole point. So in the early days, it was much easier to make calculations from single stellar models, where people just assume that you have already a strip star to begin with, and then you evolve it and try to see the effect also as a function of metallicity. But then you don't have the effects from the binary interaction that I was talking about, that you have this hydrogen layer which is retained. So this is a very large difference. So we can make a back of the envelope calculation to try to estimate how many more interacting systems we expect from population synthesis models compared to the previous prescriptions. So we need to make some assumptions about the mass distribution and the period distribution, but if we make agnostic estimates, we can say that at solar metallicity we have 2 to 3 times more interacting systems, and at lower metallicity 10 to 20 times more interacting systems. Okay, so take-home points on this part. Strip stars can expand to giant sizes depending on how much hydrogen they retain. So that's 10 to 100 solar radii at solar metallicity, and more than 400 solar radii at lower metallicity. Many more systems will interact again than computed in population synthesis models, and this will have consequences for example, for the rates of double neutron star systems, and also for their metallicity dependence. So let me briefly talk to you about 2 other ongoing projects I have on supernovae explosions and supernovae light curves. Okay, supernovae explosions. So most models, they try to do detailed, self-consistent calculations of the explosions of stars, rely on single stellar models. This has to do with how easy it is to compute these things. But you may ask, yeah, well, what is the difference? Is there a difference if there is a star which is single, or a star that is in a couple? Is there a difference in how they die? Right? So this project is about how being single, or in a binary, affects the death of massive stars. So how do we do this? So the method is to compute the evolution of single and binary stars systematically. So these stars have the same initial mass, all the same initial conditions. And to do this well, to compute the evolution of stars until the moment of core collapse, is not trivial. You need quite a high resolution and a very large nuclear network. So in this case, we chose 128 isotopes. So to give you an idea, these stellar models, yeah, they take about a month to run on 16 cores on a supercomputer. Yeah. And then we give the stellar models to people who are specialized in explosion models, and we self-consistently explode them in 2D. Yeah, so this is work in progress. So I will not show any plots to you here. Well, I have a few if you're really, really interested. But I will, for now, just schematically show you what we find. Okay, so these results are preliminary. But so we evolved 20 stellar models of single stars that are the progenitors of neutron star systems. So between 10 and 20 solar masses. We have single star, we have the binary, and as I showed you before, we are mainly interested in the primary in such a binary system and how this star evolves. So both these stars are exactly the same in the beginning. And then we evolve them, and we see how they look at the moment of death. And this is what we find. So strip stars have systematically lower core masses. And their masses are also more centrally concentrated. Okay, so here people who know about cell evolution will say, oh yeah, this is obvious. And why is this obvious? Well, the strip star interacted and lost its hydrogen envelope. So this means that it was not able to burn hydrogen into helium in a shell around the core, and so the core could not grow, and you end up with a smaller core at the end in mass. Okay? Yeah. So the mass is more centrally concentrated. You can also try to understand this by knowing that these stars will typically become more compact at the moment of core helium burning. But now, what about stars that have the same core masses? Do they still look similar, or do they look different? What are their properties? So here we take a single star and a binary star that have exactly the same core mass after core helium burning, and we try to see how different they are. And we find some interesting things here. So what I show here is the core mass. Okay, so this is an idea of the mass. But what if I go to the radius? Okay, this is absolutely not to scale. The single stars should be much, much, much larger than this. Yeah? And basically what we find is that the cores of the single stars are smaller than those of the binaries. And this has to do with the effect of the hydrogen layer on the structure of the star. In addition, we find that strip stars have higher carbon to oxygen ratios, and they seem to explode more easily. So this is exciting. Stay tuned. Okay, so I hope that I could convince you that binarity affects the death of stars. Okay. Now I will just very briefly talk about some work on supernovae light curves. So one other thing we could be interested in is what the properties are of stripped envelope supernovae from observations. And to try to understand this, we can make theoretical models to try to understand how the light curves look like just from the stellar models that we computed. And so for this, you don't need these very heavy, expensive, detailed, self-consistent explosion models. You can just say, oh, we see supernovae explosions, so apparently some stars at least explode. Okay, so you can just make the assumption that you can just create a shock inside a star and let it explode and see how the light curve looks like. This is a computation that is much more simple to make. So how I do this is create these stellar evolution models with MESA, and then put a thermal bomb inside with the supernova explosion code. And basically, you need to specify a few explosion parameters, like the explosion energy and how much nickel you produce during the explosion, and you get light curves. So now this is interesting because we can compare them to observations directly. So this is an example, supernova 2004 FE, that was fitted with a grid of lots of different light curves with different explosion parameters. And what I'm showing you here is just a proof of concept that with a large enough grid, you can start to pin down what the explosion properties are of these stars. So the aims of this project is to really probe the systematic properties of stripped envelope supernovae from observations, and to gain a really statistical understanding of the uncertainties in the explosion parameters. And we would like to provide a very large grid of theoretical models of stripped envelope supernovae light curves for use in the community. Okay, so to wrap up, stars stripped in binaries can swell up to giant sizes. This has important consequences for gravitational wave progenitors. Strip stars seem to show systematically different pre-supernova structures from single stars. We can constrain the properties of the population of stripped envelope supernovae by comparing simulations to data. And if there's just one thing I would like you to remember from my talk, it is that binarity affects the life and the death of stars. Thank you.
Questions for you?
Me?
Yes.
Okay, good. So you talked about these strip stars and their tracks through the Frischmann-Russell diagram.
Yes.
I'm just curious what happens to the other star, or is it?
Oh, yeah, to the other star, yes. So that's a good question. So the reason why I focus on the strip stars is because we understand them much better from a physics perspective. So what happens to the other star is also extremely interesting. But it relies on things we're very uncertain about. So basically you transfer matter to the other star and it accretes hydrogen. So hydrogen is nice because, so typically for the binaries I showed here, they are still on the main sequence. So adding more hydrogen adds more fuel to the stars. So they can live longer, which is nice, right? And they get brighter too. Another thing that happens when you transfer mass from one star to the other is, as I mentioned before, you transfer angular momentum. So typically what we expect is that these accreting stars also spin up during the accretion process. And so the problem is in these binary evolution calculations, it is still unclear what the details are of how you transfer matter on the outer layers of a star. So matter that leaves one star has different properties from the outer layers of the other star, and that this can lead to problems. And also it is uncertain for now how much of the matter will actually be accreted if you will first form a disk around these stars. And so there's so many uncertainties still that we prefer to focus on the stars, on the binary products we really understand today, and that is the strip stars. But it is very interesting, yes. So typically they look rejuvenated. They look like stars. They look brighter. These accreting stars, they look brighter than they should be for their mass. These are rejuvenated stars.
Do you believe your result?
What do you mean?
Like, you're using MESA.
Yes.
Large part of the community doesn't believe in the result that MESA produces, and it doesn't match with 3D simulation. So maybe you're
Yes.
replacing one wrong result with another wrong result. How confident are you?
Okay, yeah, that's a fair question. So how much do we believe 1D simulations? That's basically what you're asking. When you know that 3D stellar evolution would be the way to go. So first, it is currently impossible to simulate stars in 3D. It would take, if you wanted to do this, it would take more than the age of the universe to try to compute one single star of 10 solar masses up to the end of its evolution. And the reason for this is that you need extremely small time steps to actually be able to resolve the inner layers and the inner convection inside stars. So we have to rely on 1D calculations, unfortunately. And if it was possible in 3D, I would gladly do it. So this means we need to make assumptions, and we need to understand what the uncertainties are in our calculations. So I certainly don't believe that these calculations are exact and can tell you exactly the evolution of one particular star. But I think the trends that we see are robust. So one of the biggest uncertainties is that we assume, is how we assume diffusion inside the stars and convection inside the stars. We use mixing length theory, which is a big problem, but for the timescales we consider it should be fine. And then there's a few other uncertainties that I didn't mention yet, but I have a few backup slides on this. And that's, I showed you these binary systems, and they were computed for only one orbital period, and for only one assumption of the winds, of how the winds also strip the star. This is a very big effect. So if we vary these parameters and we still find consistent results, I think it means that our results are at least robust against these uncertainties. So what I show you here is how the orbital period affects the evolution of T stars. And we can see that depending on the orbital period, the stars will transfer matter later or earlier, right? There is this blue track that transfers matter already during the main sequence. These are stars that have very, very different properties, so that's disregarded for now. If we look at the other tracks that do what we call case B mass transfer, so mass transfer when the star is burning hydrogen in a shell, we can find that the properties of the strip stars are extremely similar on the HR diagram. And also, the place where they die is very, very similar. So in principle, this shouldn't be such a big problem. Now, the effect of winds. So one thing that I didn't mention is, so stars have winds, right? Especially massive stars have very strong winds. And these are also important to strip the outer layers of stars. And that's one of the main uncertainties in stellar physics, I think, right now, that we don't know the winds of stars, especially not the winds of strip stars. We just don't know. We have some ideas from the observations, but it's still very much unconstrained. And so when we do stellar evolution models, we have to assume some factor, some number, and it's very uncertain. It's very unsatisfying. But if we vary this wind mass loss rate, we can try to see if the results are still robust. So that's what I do here. So at low metallicity, I told you there is this hydrogen layer that is retained. And we know that from observational evidence that winds of stars scale with metallicity. This has to do with the fact that they're mainly driven, line-driven. So if you have more iron peak elements, you will have a higher opacity in the outer layers and drive the winds stronger. But at lower metallicity, we typically assume that the winds are not so effective. So what I do here is, let's for now just focus on the blue model. That's the standard model in the paper. And the red dashed line shows you a model where I used exactly the same star, but I used the solar metallicity wind. And we still find, well, that the radius evolution is a little bit different, but the final radius is still extremely similar. So the point I was making, that strip stars expand to giant sizes, is robust against variations of these parameters. I hope this answers your question.
Are you cherry picking the variables you're showing?
Cherry picking? I don't think so. I think these are really the main uncertainties we have for these stellar evolution models. As I told you, the fact that we're using mixing band theory, that's the biggest uncertainty we have for now in 1D stellar calculations. But we don't have a better way to do this until we get better constraints on how mixing happens from 3D calculations, and that is still work in progress.
Last question.
So one thing that I think would, I just want to make two comments, one of which supports what your results here, but the other is this question of robustness.
Yes.
You know, to show robustness, I think one would need to actually do the calculations other ways.
Sure.
And show that, because if you just use MESA
Sure.
again and again for different parameters, you don't know what would happen if you didn't use MESA. So I think that's one thing that we need to keep in mind.
Mm-hmm.
But I think some of these results can probably be understood in terms of basic physics.
Yes.
So for example, I don't find this result about the final radius at all surprising.
Yes.
Because there are other situations where we see this.
Yes.
So for less massive stars, we have a lot of evidence that their final radius is pretty much, even if they've been stripped, even if they have hardly any envelope left, they achieve a final radius that's very like what they would have done had they not been transferring mass beforehand. And we know that because we can measure the orbital periods that the core of these stars find themselves in, and those periods are consistent with having a large star exactly what you would expect.
Yes.
So that comes from some basic physics.
Mm-hmm.
I don't know that it's ever been explicated, you know, as clearly as we would like.
Yeah.
But I suspect that if instead of just looking at different MESA results, you looked at some of these key results and said, okay, what does the physics tell us? You would then actually have a reason to understand why not only would it be robust with MESA, but it would be robust if you tested it with higher dimensions. That,
Yeah.
you know, you can predict that some of these things will work
Yes.
for three-dimensional calculations.
Yes,
If
definitely.
you can get back to the basic physics
Yes.
of it.
Thank you very much for these points. Yes, I should have mentioned this. Obviously, we also compare it to work from other groups who use different calculations. Yes, so I don't know how completely independent these calculations are. That's maybe a question you could ask. But we find very similar results. So as I showed you, even in the 1970s, right? From a group in Russia who wrote a paper in Russian that I cannot understand, you can still see from the figures, it seems robust, right? Just from basic physics. And another point that you mentioned, and thank you for that, is comparing to observations. I think that's where we can do good science, right? And really try to understand something about the universe when theory and observation come together. So you mentioned some results where we see stars that are large and that have very little hydrogen. And another thing I'm really interested in is the stripped envelope supernovae. When we make, when we fit these stripped envelope supernovae with different models that have different sizes, well, we can get an idea of the size, right? We can get an idea of the uncertainty. So I think by really looking at the population of observed stripped envelope supernovae and comparing these to the stellar models, we will get an idea of what the exact properties of these things are.
All right. Let's thank Eva very much.
Thank you.